I'd like to recap a bit from last Tuesday. The message I wanted to give you is a very simple one, that the hydrophobic effect, you can say, of course, that water loves water, that apolar systems also like apolar systems, but it is not true that apolar systems and water hate each other. In fact, there are many cases where the enthalpy of dissolution of a nonpolar solvent in water is negative. It should be very mild, but it can be negative, as we shall see. It is, many people use apolar and hydrophobic as synonyms, and they are not, indeed. We saw that the entropic effect, in fact, was due to water, and it is because water loves water a lot. So for water, you don't necessarily have to be a great lover. And at the end of this talk, or maybe tomorrow, I'd like to convey the picture that, okay, you don't have to be a great lover, but yet you still should meet certain thresholds. Well, we saw that the hydrophobic interaction, in fact, was due to the solvent, and it was when you solubilize a nonpolar substance in water, there's a decrease in entropy, and this decrease in entropy is due to the fact that water around the nonpolar solute is more ordered, and it would prefer to go to the bulk. Here in this table, we saw that this is the free energy change that is, of course, for these nonpolar systems is always positive. But the enthalpy change can be very small or even negative. So the great contribution to this positive free energy change is due to the change in entropy. And this is due to the solvent. This unfavorable contribution becomes from a negative change in entropy due to water. This is, for example, a simple case where a small molecule like neopentane is transferred to water, and you see that this is very typical that around room temperature, the change in enthalpy could be negative. So there is hydration. Water hydrates the nonpolar substance, but the entropic contribution is huge. So you're going to have a positive change in chemical potential. Okay, let's split this. The existence of hydrophobic hydration produces a decrease in the entropy of the solubility of the hydrophobic substance, since, as we saw before in Tuesday, dynamical and structural studies tell us that nonpolar solutes induce a restriction in their hydration water. These water molecules are more ordered, and this produces an entropy decrease. In fact, when you have two nonpolar solutes in water, these two molecules are hydrated, and they tend to aggregate in order to free this hydration water to the bulk where they're going to be more comfortable. So this is the basis of the hydrophobic effect. It's like an interaction. It's not an interaction. It's a collective phenomena, but it's due to the fact that you are releasing water that is more restricted around the nonpolar solute to the bulk. And it is a non-trivial effect since it responds in non-trivial ways to changes, for example, in temperature or pressure. We always saw this on Tuesday, but perhaps it's a bit far away. So this is also, this is the case of two small solutes. This is a potential of mean force, a sketch of a potential of mean force for this case. When you have these solutes far from each other, they are both hydrated. And when they become too, you are going to have a minimum here. It is the case where you are liberating water to the bulk, but in some cases, you also have a barrier here. This is due to the fact that there is a cost in releasing these hydration molecules. These molecules are attracted to the solute, and you need to overcome a small barrier in order to go to the minimum.
Is this a type of depletion?
Sorry?
Is this a type of depletion? Because usually in depletion you have big parts.
No, this is not depletion. I spoke of, oh, sorry, depletion when you have, for example, that was on Monday's class, where when you have a very small solute, it's going to be hydrated. When the surface, the nonpolar surface is extensive, if it is perfectly flat and repulsive or not attractive at all, you are going to have some kind of depletion in density, since water is going to be repelled. And this, I show a picture on Monday. But if the surface has some kind of structure or is a bit attractive, you're not going to have depletion at all. I saw a picture, and I think that later on I'm going to show one more. So if you have two nonpolar surfaces, they are going to collapse. You are going to have a hydrophobic collapse, but if you have only one, it's going to be hydrated. In some sense, it is as if water abhors vacuum. It has to hydrate the surface. Concerning the effect of temperature on the hydrophobic effect, there are, in fact, two opposite tendencies at play. Of course, if it is an entropic effect, if you are increasing temperature, the hydrophobic effect is going to grow. But this change in entropy is due to the solvent, and it is the difference between the solvent when it is hydrating the nonpolar solute and its the position in the middle of the bulk. So if you increase temperature, you know that water's structure begins to be looser, and so this change is going to be smaller. So this increases, but this could also decrease. So the change is not trivial, and in fact, there could be a certain temperature where the effect could also be reverted. This is, in fact, what happens with pressure, since pressure makes, if you go to 1 or 2 kilobar, water loses completely its regular structure, and then you are not going to have much change when going from the hydration of the nonpolar solute to a bulk place where you don't have structure at all. Water is losing its hydrophobic effect. There are also other factors which modify the hydrophobic interaction, like the introduction of substances that induce structuring in water, or substances that destroy the structure of water. Okay, I think that was the point where we left on Tuesday. How do you measure or consider the hydrophobic effect? I'm going to speak first of certain measurements or certain quantities that have been developed more in the biophysics community, but then we are going to move to another quantity that is more used in material science. One of these measures is the consideration of the atomic solvation parameters, ASF. which considers that biological molecules in general are not completely polar or non-polar. They are amphipathic. They have both kinds of behavior in general. And this amphipathicity is going to change its properties when you are, if you like to calculate the hydrophobic effect, you have to take into account all these different contributions. And you have to sum up all these contributions that can be contradictory. So Eisenberg defined this atomic solvation parameter, considering that the interactions of water and the solute can be considered as the sum of this parameter, describing the interaction of each atom of the compound of interest. So you roll, for example, a water molecule on the surface of the nonpolar solute. You calculate the surface exposed area of the molecule, that is not the area of the whole molecule, since there could be excluded volume effects. And then, if you are able to estimate the interaction of each atom with water, which are taken into account in this quantity, that is the solvation parameter, then your change in free energy is going to be given by this change for each atom would contribute with its own change and the area it has exposed to solvent. Of course, if you're going to study a large system, like, for example, a protein, you're going to have to sum over all these atoms exposed to the solvent. This should be the case. For example, you have here a small water molecule that rolls over the surface. This is the surface accessible water accessible surface. And then you're going to sum up all these contributions. In this sense, you can build a hydrophobicity scale, which considers all these effects and considers that certain regions of the protein are going to interact and others are going to be screened. For example, this is a table. If you see here are the different amino acids in a protein, and these go from the most non-polar amino acid, isoleucine, for example. It's a very big non-polar molecule. And here you have the charged ones, arginine, lysine. You have glycine should be in the middle. It has its side chain is null. It's a hydrogen atom. And of course, you have alanine close to glycine. It's only a methyl. And here, for example, you have histidine or so, which are not charged but are polar. Okay. This is very important for people working in protein folding, since in this way you can evaluate the area accessible to the solvent in the protein and calculate the difference in free energy between the two states, which would be the folded state, and a reference state would be the random coil or the unfolded protein. And in this sense, you can calculate the free energy change due to the folding of the protein. Well, another possibility would be to introduce what are called hydrophobic moments. These are defined in a similar way as the case of interactions with electric charges. You define these hydrophobic moments, mu sub h, considering that there should be a momentum that could be calculated. For example, the zero order of this hydrophobic moment would be the hydrophobicity value. And if you have an amphiphilic molecule, a molecule that has a polar and a non-polar region, the first order of this hydrophobic moment will depend on the distance, and it could be basically calculated like a vector, like in the case of charges. For example, the hydrophobic dipole could be represented like a vector that goes from the polar region of the molecule to the non-polar one. For example, this is arginine, and you're going from the charged region to the alpha carbon of the side chain. In this sense, you can construct the hydrophobic moment, adding up all the dipole components in a vector way, and so you can build also a table in where you are going to see again, glycine in this case would be 0. There's no dipole, of course. And then you're going to have here large values for the highly charged residues like arginine or lysine. And it's used to be shown in this way, pointing from the charged side of the molecule towards the alpha carbon. Okay. Another way to measure or to estimate hydrophobicity is, of course, by means of partition coefficients, where you are basically measuring the free energy transfer of a nonpolar solute from its phase into the water phase. This can be done experimentally, and this is, for example, this is a sketch where you are here you have a molecule, a nonpolar molecule in its own phase, and it's transferred into a water phase. What you do is you define a hydrophobicity scale by defining these partition coefficients, which would be you are going to obtain then when you consider the balance between or when you compare the chemical potential in its own phase. 0 would be the hydrophobic phase, and its chemical potential in the water phase, which we use the index W. So the change in in chemical potential would be related to the logarithm of this concentration, this x0 over xW, and this is going to be called P, the partition coefficient, so that delta mu is going to be related to the logarithm of P. And it would be an energy of transfer. Of course, this is going to be a non-universal scale. It would be a relative one. But in this sense, if you use a solvent as a reference, you're going to be able to construct a hydrophobicity scale. But if you change the solvent, you're going to build a different scale. Scales are going to be similar, but there can be certain differences and certain alterations in the order of the different nonpolar substances. But this is the advantage it has is that it is not calculated, you can do it experimentally. This is, for example, one of these scales where you go again from the very hydrophobic residues to the very hydrophilic ones. In this case, I think it was cyclohexane water. And it is also interesting that, of course, this is related both to hydrophobicity and hydrophilicity, and it would, in some sense, tell you on the amphiphaticity of the substance. Okay, and as said here, if you use different solvents here, different nonpolar solvents, perhaps you are going to obtain different, some alterations here in the order of some of these amino acids, but in all cases, you're going to have the hydrophilic here and the non-polar at the top. In the same way, people used to define a hydrophilic-lipophilic balance. This balance can be related to, is a measure of the amphiphaticity of the molecule or also empiric, and they have been derived when related to the partition coefficient, that this hydrophilic-lipophilic balance is related to the logarithm of the inverse of the partition coefficient. Hydrophobicity, of course, is a non-specific interaction. Hydrophobicity is not made of bonds, so there's no specificity. But in certain cases, for example, in biology, you can have certain hydrophobic interactions that bear certain specificity. For example, when you have two different surfaces whose shapes are complementary. And this can be important, for example, in the field of drug design or protein-protein interactions. And are related, of course, to the geometry of the different molecules which are considered. This is an area where there's a lot to be done still, since, of course, you know, we show it 3 different scales. There's no consensus at all in this field, and there are a lot of empiric developments that could be improved. Okay. I would like to move now to another measure, which we're going to employ later on, maybe more tomorrow, that you can calculate when you do molecular dynamics simulations, for example. That is a way to quantify the hydrophobicity, for example, on a surface. Here, we are going to focus on systems that are going to be very interesting for us, which are self-assembled monolayers. I think I spoke a bit on these systems on the last lesson. They are basically, they can be built experimentally. You have, for example, a crystal of gold, and you, with a tile bond, you bind alkyl chains, which can be functionalized at the end, and these are going to interact with water, for example, in our case. So you're going to have a monolayer of long alkyl chains, which can be functionalized in order to get, for example, in this case, you can get a battery, a range of a whole spectrum of hydrophobic or hydrophilic behaviors. And we are going to, this is, for example, one of these cases. These are the chains, and you can put here different functional groups, and these are going to be in contact, for example, with water. And what we are going to do is to study what happens with water number density fluctuations in regions or observation volumes, which are going to be placed tangent to the surface. And for example, in this case, this should be a very small sphere of the size of a methane molecule, 3.3 angstroms, for example. And we're going to study what's happening with water in this region. And this can provide us of a very interesting measure of hydrophobicity, and also can be very instructive on the way that water is interacting with this surface. Okay, as we said before, water tries to hydrate these surfaces. Here we have different, for example, different of these self-assembled monolayers. They are going to the hydrophilic, to the hydrophobic, to the hydrophilic ones. For example, in this case, is when you have a methyl here, which is hydrophobic. And for example, in this case, you have a hydroxyl here. So this is the hydrophilic side of the spectrum. And you have many of these surfaces arranged in a way from hydrophobic to hydrophilic. And you look here, there are not interesting changes. Most of them behave very similarly. In all of them, you see layering. Maybe in some cases there are smaller peaks, but in all cases you have a first peak close to the surface, and you have also more structure, which says that water, there's no water density depletion. The surfaces are going to be hydrated. So the density is not an interesting measure. Number density is going to be basically the same if you have here a methyl or if you have a hydroxyl. But what is going to behave quite differently is the way in which water fluctuates around such mean values. The mean value, n, is going to be constant, but if you have a hydroxyl here, fluctuations over the mean value are going to be small. But if you have a nonpolar group, like methane, for example, methyl, the fluctuations are going to be large. So the mean value, this is not the size of this, or this is not the size of this sphere. These are bigger spheres or bigger observation volumes, but you see that basically the mean value is the same in both cases. The difference is given by the fluctuation, of water number fluctuations. What is telling us this fact? It means that if you are close to a hydrophobic surface, you are hydrating the surface, but you are not comfort at such surface. And it would be easier to have a fluctuation in which you are being able to have a cavity here. So these water molecules here are less comfortable here and are going to be more easily taken to the surface, so the system could be dehydrated. For example, if this surface is going to interact with a ligand, for example, this ligand would need to replace the hydration water, and in this case, it's going to be easy to replace these water molecules, and here no. Here it's very difficult to remove. So in this case, these fluctuations can give you an idea of the work you need to dehydrate the surface, the work you need to create a cavity. And in some sense, the probability of having a vacuum here, the probability of cavity creation in the observation volume, is going to be proportional to the free energy of the work to remove water. So this is proportional, and of course, this is inversely proportional. Here, for example, we are plotting this hydrophobicity scale in the sense that, for example, this is the case of hydroxyl, and this is the case of methyl. For the hydrophilic surface, the probability of cavity creation is very low. And for the case of the, here is n is 0. So here is very low, and in this case it's higher. So it is easier to remove water, and that tells you on the hydration propensity of the surface, of its hydrophobicity, on how easy or difficult it's going to be for you to remove water, and if you are a ligand, to bind to the surface. So this is a very interesting measure developed by the group of Shekargarde that we are going to use. Okay.
You have huge fluctuations. The size of the fluctuations scales with the sigma. You have a huge fluctuation when you have large sigma.
Mm-hmm.
If I go even larger sigma, my fluctuations will be larger or not. You just have to store regime.
Sigma squared fluctuation. If you go to larger
volumes, yeah,
larger volumes.
But then you can create a space,
Mm-hmm.
like a space away
Mm-hmm.
from water from the surface
Mm-hmm.
that scales with these two or not?
If it scales with
I have the water. You're saying
yes,
that then you generate
a cavity.
a cavity. Is this cavity related with the sigma? Or is always the same, is related to the water size? Water interaction with the surface?
Of course, if your observation volume is larger,
Yeah.
the probability to create a cavity goes down.
Yeah.
It's even more difficult. But it would depend on what you are approaching. For example, if you have two of these surfaces, if you have two of these, monolayers with hydrophobic residues here, and they are approaching each other, they are going to collapse. You're going to have the hydrophobic interaction. Water hydrates the surface, but if you approach two of these surfaces, you're going to see this perhaps tomorrow, but they are going to collapse. At the end, if you calculate, for example, a potential of mean force, it's going to give you a minimum, of course. But that depends on what you are, if you are approaching a surface or not. If you ask me, is it possible to create a large cavity? No, it's very difficult if you have one of these surfaces isolated. But if you approach two of them, of course, what is going to go out? As it happened, for example, in a carbon nanotube, in certain cases, as we shall also see. Okay. Let's speak also of another experimental measure, which is the standard in material size on cell surfaces, the contact angle. What people do to measure the hydrophobicity of a surface is to put a drop of water over a planar solid surface and measure this contact angle here, that in the case of a hydrophilic surface, since there are good attractions between the surface and water, this is going to spread here, and so this angle is going to be very low, close to zero if it's very hydrophilic. In the case of a hydrophobic surface, this angle is going to grow. There is a consensus that at 90 degrees, you are in a transition from hydrophilic to hydrophobic. And at certain point, you can also have larger angles. You can have super hydrophobic regimes. You have 150 or 60 degrees, for example. And these measures have been done experimentally on the battery of self-assembled monolayers I showed you before. And they were compared with molecular dynamic simulations done for drops deposited on these surfaces. You see there's a nice linear relationship, but there are certain discrepancies. For example, here, this is the cosine of the angle, so this would be 90 degrees. So we are speaking here of a hydrophobic region here, and the hydrophilic regime in the top part of the picture. And this is the prediction from, this is the experiment. This is the experiment. So this could be hydrophobic, and this region would be the hydrophilic region, and these are the predictions for molecular dynamics. And you see that here, for example, these two systems are predicted, are in fact hydrophilic in the experiment, but when you look at the simulations, they are going to be predicted as hydrophobic. But a linear relationship also holds. And this is the measure, I think it's a more common measure in material science. But there was a commentary which was very popular that said that hydrophobicity depends on the eye of the beholder, in the sense that this is a very common definition. Everybody presumes that knows what hydrophobicity is, but not everybody is talking of the same thing. And not everybody is able to say, well, I can give you a reason why this surface is hydrophobic or this surface is hydrophilic, or it's very difficult to find which are the fingerprints of hydrophobicity or hydrophilicity. Even this change here in 90 degrees is what people take as the limit between hydrophobic and hydrophilic. But these people said, well, nothing dramatic changes. There's nothing, we cannot observe anything interesting when you change from below to above 90 degrees. In that case, this is just an arbitrary definition. It's consensus. Well, that was our question, precisely. Yes, of course, it should be related to interactions. And of course, when you go to at this place, you are going to form, for example, the hydroxyl or the amide. You are going to form a hydrogen bond. That's the optimal situation. You are replacing a hydrogen bond for water. Everything is very happy. And here you don't have hydrogen bonds, and you are going to disrupt at least one hydrogen bond of the. You do simulations in graphene or so. You say water tries to orient only one of its sides, tetrahedral sides, and tries to keep the other three formed with other water molecules. So it lacks the less hydrogen bonds as possible. It loses one. But, well, in the middle, it's not so easy to see what's happening in the middle. So it should be related to, of course, to interactions. And that's what we saw. We were going to revisit this, but probably tomorrow. Okay. Okay. Well, but before doing that, I have to also recap to the classes I gave on Monday, where, if you remember, we introduced a structural parameter for water, which was based on energy instead of using geometrical constraints, which worked well for water, but could be only used at bulk water. The idea is, well, it could be interesting to have some kind of indicator that could be used generically at any situation, which could be valid, for example, at hydration and nanoconfinement. As far as I know, there are no indicators which are capable of being used in such situations. In fact, many people have used them. We commented a paper where they they used one of these indicators, but they are if you are based on geometrical considerations, when you are imposing a geometric constraint given by, for example, by a surface, that's going to spoil your definition. And if you use a definition that was derived from bulk conditions, perhaps you're going to get artifacts. And maybe there could be certain signal, but I can assure you that you are introducing artifacts. So since we developed an indicator that was based only on energy considerations, that was even parameter-free, it was a good idea to move to these kinds of conditions, of systems. But, of course, we had to redefine it, since this index is also only valid for bulk conditions. You remember basically what we did here was very simple. We consider a water molecule as a central molecule. We look at its interaction with the rest of the water molecules and order them in decreasing order of their strength. So the first one would be the water molecule with which the central one interacts more strongest, and so on. So you would have a B1, B2, B3, B4, and we decided that, or we noted that the fourth one presented a very neat modality. This was done within the inherent structure scheme that Paola told you today, since this enabled us to extract or to erase the blurring effect of thermal fluctuations, which prevent you to decide whether one structure is really, one molecular arrangement is really a defect from something that is merely deformed. And we found that this parameter had a distribution like the one we show here, this for P 2005, and you have two peaks. One of them is related to molecules which basically are very well ordered in a tetrahedral manner, where they have 4 linear hydrogen bonds. And here you have molecules where this tetrahedral structure is distorted, and they mainly lack a hydrogen bond. And you have these two kinds of molecular arrangements, which, when we look at their radial distribution functions, were really they resemble very well what you see in HDA and LDA, which show with Paola today, and also myself on Monday. So we decided, well, it's nice to try to improve or to modify this index in order to make it generic, so that we can use it in different situations. For example, in surfaces, like the one I showed with you before, or it could be interesting for bidimensional systems like graphene or carbon nanotubes, or also for proteins, and that's what we did. Okay, well, this to recap, but I already spoke of this, and this is truly good scenario that Paola told you. Let's go here to the index. Well, the idea was to consider what's going on in terms of structure and energy when water builds its hydrogen bond network. You know that this is very well known, that contrary to normal liquids, which in normal liquids, when you want to improve energy, you want to go down in energy, what do? You shrink and try to have as many contacts as possible, so you're low in energy. There is a contraction of the structure, where water is anomalous in this sense, since water expands its structure, of course expands its second shell in order to improve its tetrahedral order at the first shell. So if you want to have well-formed 4 hydrogen bonds, you need to have a gap between the first and the second shell. This expansion is what allows you to be well tetrahedrally ordered. And this is, of course, is completely known, this second shell expansion. And this is what allows water to form a very extended hydrogen bond network. But this is not the whole story, since, as we shall see now, as water has defects, coordination defects, and these coordination defects have to live in a very expanded structure. How does water manage to combine these two possibilities? So our answer was that since water presents a strong reluctance to lose tetrahedrally directed hydrogen bonds, anytime a water molecule resigns one of these interactions, we expect some directional energetic compensation to this hydrogen bond loss. This should result from the need to avoid the presence of partial charges in the, for example, if you are losing this or a hydrogen bond here or here, the partial charges you're going to have here in a very extended structure should be compensated. If not, you are going to have these charges, you need, in some sense, to compensate this energetic loss. So we now decided to build a new metric we call B4S, since we are going to look at 4 sites now around our water molecule. In simple terms, what we did was to take a water molecule. For example, here you have the oxygen, the 2 hydrogens, and the 2 regions of where the lone pairs would be located. And we force it to be tetrahedral. If you are, for example, in simulations, you have different water molecules. If the water molecules are already tetrahedral, like SPCE, it's fine, it's okay. It's already tetrahedral. But if it is not, since certain models have an angle that differs a bit from the tetrahedral angle, well, we open a bit the angle in order to have a tetrahedral configuration. And we have 4 directions we put 4 points at around 1 angstrom of the central molecule at each of these tetrahedral points. So we build a perfect tetrahedron around a central water molecule. And then what we did was, okay, let's look at a sphere of around 6 angstroms around this central water molecule, which is basically consistent with the second peak of the radial distribution function, water. We also used larger values, and we showed that it converges, so 6 angstrom was okay. And we decided that these 4 points are going to partition space into 4 regions, in the sense that at each point, we add up all the interactions that this central molecule is forming with the rest of the water molecules, which are more nearer to this point. At each point, we look for the water molecules that are closer to this point that than any other one, and we add all these contributions to the interaction. We consider both Coulomb and Lennard-Jones interactions, and then we are left with 4 points which have different, a different interaction. And we order them, sorry.
6 angstroms do you choose based on the center of the sphere? So you're trying to get in the first.
We wanted to have include both the first and at least the second coordination sphere. But we also performed it with larger distances, and at this point, basically, it converges. So there's no point in going. But it's easy, it's cheap to calculate, so you can use a larger threshold, it's okay, but it's going to work basically in the same way. Okay, and when we are left with these 4 points, we order again them from the most negative, where you have more attraction, to the less negative one, from the strongest to the weakest one. And we define the B4S as the weakest of these 4 points, the site where water molecule feels the weakest interaction. This is, for example, I don't know if you can see it very well, but here you have a water molecule that is in contact with other water molecules, and for example, a graphene structure, and this would be the sphere, and you have the 4 points, 2, 2, and the other 2 here, and well, you calculate all the, you adapt all the interactions and consider the 4 points. Yes? Mm-hmm. Well, the models are flexible, but not that flexible. So perhaps if you define the 4 points, you are not going to, of course, they could change in time, but perhaps I think it's going to work perfectly well. I don't expect large changes, since you know, these 2 points, for example, coincide with the hydrogens, and these 2 the lone pairs, but we are putting them at 1 angstrom here. This is the position of the hydrogen. But what we are doing, in fact, is we're defining 5 radial regions, this partition space in 4 regions, and you see, well, which water molecule belongs to one of these 4 regions, and add up all the interaction. That could be the
If your surface is closer than the 6 angstrom, suppose you have a molecule, you just get part of this.
Okay, you are going to feel the part of the surface, and for example, here in graphene you have water. Perhaps you can have water here. Maybe you can water the other side. But I think that in that case you're not going to feel the water that is in the other side. But for example, I'm going to show very briefly something we did with Mateus, Rafael, and Patrick on carbon nanotubes, which were double-walled carbon nanotubes. This water molecule is going to fill the first layer and a bit of the second. Of course, the inner nanotube is going to be farther away, so the interaction is going to be very weak, but it's going to count in our index. So it senses around 6 angstroms from the molecule in each of the 4 sites. So whatever you see there is going to impact in your site. So first, what we did is to apply it to bulk water, and these are the results. Here you have the distribution of the index for bulk water. This is, well, in this case, this tip 3P, but here we have tip 4P 2005. And this is the kind of result you get. You have a distribution that shows signs of bimodality, since you would have a peak here at a region that is consistent with basically one hydrogen bond, one linear hydrogen bond, and you're going to have this region here that you have a shoulder. This have signs of bimodality. And to see which kind of molecules are contributing to these two regions, we decided to take a look. Well, the previous index, the B4, was better at, sorry, we are also using inherent structures here to get rid of the thermal noise again. And we decided to, well, let's look at the two kinds of molecules that are basically, there are the molecules which are tetrahedral and the molecules which have a distorted first shell. And most of them have lost one hydrogen bond. So this region is going to be to have the contribution of molecules with molecules with 4 hydrogen bonds, and here it could be the ones which lack one of them. Since we are looking at the fourth site, when we are just, here is just bulk water, you are going to feel one hydrogen bond here in the tetrahedral molecules, and the rest could be the contribution of the second shell. But the second shell has expanded. So if you make the calculations, I did not show them here, you find that this is basically the hydrogen bond contribution, and the rest are adding very low values or even nothing. So this is basically an effect of the first shell. Whilst in the case of the D molecules, here we're showing what you get with the T molecules, the tetrahedral molecules, but basically are here in the peak. And this is the plot for the defective molecules. In the case of the defective molecules, you're not going to have a hydrogen bond at that site. So there's no contribution basically of the first shell, all the contribution from the second shell. But in this case, the second shell, as we show, this is for an example, the second shell has contracted in order to compensate the hydrogen bond loss. And this is not trivial, since, you know, this peak is here at around -6 kilojoule per mole. It's 1/3 of one hydrogen bond, or 1/2. So this is here you feel the contribution of one, or in most cases, more than one molecule, which belong to the second sphere, that unlike the case of the tetrahedral molecules, where the second sphere has expanded in order to allow for the formation of a high-quality hydrogen bond, here, since you have a lacking site, the second sphere has contracted in order to compensate partially the loss you have by the lacking site. This is at high temperature, and here we are showing results for this other water molecule. This is with minimization, and in this case, we are showing the case without minimization that is similar, but we decided to keep this one since it classifies better and it works much better, more when we move to surfaces. So we are still paying the cost of doing the minimization, but they are not very costly. And here we show these are different temperatures from low to high temperature. This is the case where we are we have the distribution of the index without normalization, and here we are sorry, we are looking at the contribution of T and D molecules. Without minimization, this is the population of the tetrahedral molecules. This is for the population of the defective molecules. But of course, as I showed with you on Monday, the tetrahedral molecules are prevailing. They dominate. The population is very large. You have to go to 300 Kelvin to have around 20 and 30% of the molecules. So the T1s are dominant. So here we show the same data we show here, but for the case where we normalize both distributions to unity. So here's the distribution for the T molecules for different temperatures, from lower to higher, and here the case of the D1s. And here again for the non-minimized configurations. You see the result are very similar for all temperatures. What you are going to have is less defects as you, of course, as you cool down. And this peak improves as expected with supercooling, since you are improving the hydrogen bond. But this peak is rather temperature insensitive, and also does not depend much on minimization. It looks much more like an entropic effect. And it's very nice that in all cases you have the same value. You have a compensation that is not trivial. You know, KT should be around. This is around around 2 or 3 times KT. So it's not negligible. It's a large value. It's not as good as being here, but it's a compensation. This shows us that water has some kind of fine-tuning between structure and energy. These two things interplay in order to accommodate the first and the second shell. When you have a very well-structured molecule, a tetrahedral molecule, there is a second shell expansion. You improve energy by expanding your second shell. But when you have to lose a hydrogen bond, and this happens in most cases as temperature goes up, you can compensate it by contracting your second shell. Yes, the two kinds of structures. This contraction of the second shell provides you partial energetic compensation to these molecules. In this sense, this case, the molecules in this peak would be LDA-like, low-density amorphous size-like, since they are the T molecules that we showed before were very similar. They are GDR as LDA, and this is exclusively made of D molecules whose radial distribution function is very similar to HDA. And this value is quite attractive, much larger than KT. So this tells us an interesting message, since water has two demands, two requirements. Either you satisfy the hydrogen bond, that would be the most likely situation, or if you are going to lack a hydrogen bond, you have to compensate it. So in some sense, you are establishing an extended network, but on the other side, you are allowing for the existence of defects, which could be extremely costly in a very expanded network. If you have a very expanded network, you're going to have a defect isolated in that network. It would be very costly to have it in that way. So it's better to locally contract in order to compensate. Like This, for example, this is the central molecule. These are the three ones with which it is coordinated with hydrogen bonds. And these ones are molecules from the second shell, which I show with you that populate the intershell region between the first and the second shell, and which are, in some sense, compensating the lack. This is an evidence of a molecular principle that would be underlying the existence of these two molecular arrangements that are compatible, for example, with the two liquid scenario. Considering the two liquid scenario, there was a recent review by Finney who said, well, okay, while the two liquid description would be very interesting and relevant concerning the behavior of water at low temperatures, what about high temperatures? And does it tell us anything in real life? What's real when for water interacting with other systems? That was his question. And okay, for example, this could be one first answer to this question. In the sense that we elucidated the existence of fine-tuned interplay between structure and energy. And this is valid at all temperatures. We show it from supercool regime to room temperature. You see the peak, the same peak in all cases. It does not change with temperature. So this effect is occurring, and this principle underlies in some sense the molecular arrangements that would be responsible for the HDA and LDA phases. However, we should say that this is compatible with the two liquid scenario, but our results are not dependent on the validity of such scenario. What they require or they rely on is on the existence of two kinds of molecules, tetrahedral and defective molecules, which, as we showed before, are similar or compatible with LDA and HDA. This is, for example, the two cases where I showed before. This is tetrahedral molecules. You have first layer, second layer, and a gap. You needed this gap in order to be unperturbed here and to form the well-formed hydrogen bonds. But in this case, when you are going to lack a hydrogen bond, you begin to populate this region. And this is not only that these molecules move here and perturb the first shell, they also compensate for their missing site. Okay. I don't know which time. How much? Half an hour?
No, we don't have a half an hour. We don't have more time.
No more time? Over? Oh, so it's a pity. Well, no, I was stopping just here. This just to tell you. For tomorrow, I plan to move to surfaces, and what we're going to try to convince you is that the same molecular principle we found for bulk situation is also operative at interfaces. In the sense that, you know, the two liquid scenario says water is one substance, two liquids. What we are saying in this case is it is one simple molecule with two interaction demands. It has two requirements, two different requirements. Or either you fulfill the better situation, the hydrogen bond, or you compensate it. And this happens for bulk water, in what I show with you. But is this also valid generically when water is in front of, is is interacting, as Finn is saying, in real life, it interacts with other molecules or surfaces or whatever, well, we're going to see that it seems to be the case that water demands this kind of compensation, that the molecule, the interacting molecule or surface, in some sense, is going to mimic energetically one of these two situations. Either it provides a hydrophilic site to form a hydrogen bond, that would be the perfect scenario, else it needs to, it needs to provide the water molecule with a compensation for the lacking site. If you are in front of a surface and you cannot form, you have to cut one hydrogen bond, okay, but you compensate it to me. So it returns to the beginning. Perhaps you don't need to be a great lover for water. You don't need to offer her a hydrogen bond, but still there are certain requirements. And the most interesting point is that this would allow us to find certain fingerprints of hydrophilicity, will allow us to find what if isn't when you change, for example, the contact angle from below to above 90 degrees, there's nothing interesting happening. Yes, something interesting, we think something interesting happened since these two requirements that the water molecule has in bulk translate for wetting situations, will translate into two limiting hydrophilicity thresholds. And these two hydrophilicity thresholds would be a saturation limit when you form the hydrogen bond, and another limit which would be the transition from hydrophilic to hydrophobic. And this would change. It would depend on your ability to provide the water the compensation or not. And that's what we are going to see tomorrow. Thank you very much.